Hi, everybody. Today I'm going to be talking you through some of the ArcGIS analysis you are going to be doing for an intensively monitored watershed located in Idaho called Reynolds Creek. When you click on the data link posted on Moodle, you are going to be taken to this screen. You're going to see the name reynoldscreek.zip. This is the name of that watershed. And you're going to go over here and you're going to say download. And it shouldn't be a massive file. It should have download very quickly, like we see here, as compared to some of the other data sets you've been working with. And I am going to plug in my personal drive. If you need to pause this to do that, go ahead. I'm going to go to my downloads folder. And it should be right there, reynoldscreek.zip. I'm going to copy it, go down to my folder here. I'm going to create a new folder. I'm going to call it homework 4 or whatever homework number this is. I think it's homework 4. And no spaces as usual. I'm going to drop the zipped file there. I'm going to extract it, which again should be relatively quick because it's not that big of a file. And we now can get rid of that .zip file. I'm going to delete it. Very quickly, I just want to show you there's a folder in there called rain, and it's got all of the information we're going to be using today. So I am going to briefly pause things and get started in 1 second. All right, your first order of business is to open ArcGIS Pro. So go ahead and do that. It might take a few minutes, and by a few minutes, I mean hopefully a few seconds. Mine takes a little bit longer. All right. When you pop up here, you're going to get the ArcGIS Pro intro scene. We're going to grab map, and I'm going to name this. I tell you to name it homework 4 Reynolds Creek. So let's call this homework 4 Reynolds Creek. I'm just going to say CR. And I am going to put this in my drive, my CE352 folder, and my homework 4 project. And I am going to say okay. And now it's going to open a new scene, new map, and we're going to start with our analysis. So we get the US. First thing we're going to do is add data, always under map. Add data, and let's take a look at what data we have. So CE352, homework 4. I've got Reynolds Creek. I've got rain, and I have a couple of different things here, and I'm going to select them all. If I hold down the Shift key, I can grab them all and say okay and go ahead and add. If it asks you to do anything, just go ahead and say yes. And we're using a projected coordinate system for this one. That's why the US looks so weird, because this is centered on the state of Iowa, so don't worry about that for now. But we just added 3 data sets. States, remember you can turn them on and off. RC out and Ray DEM. You know, DEMs mean elevation data, and then this table down here called Ray precip. So I can't see much right now. If I were to zoom in on Idaho, trying to figure out where this watershed is, I'm not going to see much, and that's because of the order of things. So I'm going to drag the state's shapefile down, and now I can start to see some things. So now I have a DEM, and I have a watershed outline. I just want to show you something really fast. If you right-click on the file and go to Properties, you should be able to go to Source, and see the cell size here, 30 by 30. It's 30 meters by 30 meters. The other thing I'm going to have you do is turn the watershed into an outline with a hollow center. So you can always click on this black outline piece. But let's say you want to change the color of that outline. Let's make it, I don't know, bright blue, and let's make it a little bit bigger width. On the boundary, I'm going to say apply Oh, that applied to the states. Let's try this again for RC out. I'm going to say no color there, and I'm going to give it blue, a little bit more of an outline, and say apply, and now I can see the DEM as well as the watershed outline. So states, you don't have to change this. I'm just going to make these black just so I can see. So before we get started, I want to turn these two layers off and show you the area that we are in Idaho. So we are in an area that is relatively mountainous. You can see the mountains cutting through here, 8,000-foot peaks, which is pretty high. And you can see Reynolds Creek, the watershed in question, the stream corresponding to that watershed sort of cutting through the middle here. I'm going to turn these two on. The first thing we are going to do is we are going to create contours. So contours are another way that we can visualize what is happening in our DEM. So we're going to go to analysis, we're going to go to tools, toolboxes, down to spatial analyst, and this is where a lot of the functions for rasters, aka these gridded data sets like DEMs, are housed. So there's all sorts of them here. If you end up using ArcGIS for another class, I would encourage you to explore these. I'm going to go to surface, and we have a couple of different options. I am going to go to contour. And my input raster, which just means my gridded data set, is going to be the digital elevation model, Ray DEM. It's giving it a new name, so contour, I'm just going to say Ray DEM to make it a little simpler. I'm going to tell you to make the contour intervals 100, and we're not going to change anything else, and we're going to run it. So again, I think DEMs are a nice way to look at data, but I want you to see an alternative way, which are contours. And here we've got a really nice looking contour set up here. If we wanted to clip this to just our watershed, again, just sort of showing you things that you can do within ArcGIS, I'm going to stay in that Arc toolbox, spatial analyst tools, and I'm going to go to extraction. I'm going to say extract by mask. So my input raster is going to be Ray DEM. My mask is going to be my watershed outline, RC out. And I'm going to call this Ray DEM watershed. So if it's a raster file I want to clip to a spatial file, I'm going to use the extract by mask feature. So we'll see what that looks like in 1 second. So it's hard to see a difference, but if I turn Ray DEM off, now you can see what's happening. And if I wanted to clip the contours instead, I'm not going to use that extract by mask feature because that is just for raster data. I'm going to zoom up and go to analysis tools and say extract and clip. So you clip when it's a point, line, or polygon, and we have contours that we want to clip. So let's clip them to our watershed outline, RC out. So contour Ray DEM, I'm just going to give it a 2. And I'm going to run it. And again, it's hard to tell what's happening. I'm just going to remove the original data set, Ray DEM. And now I have contours clipped nicely to my watershed, and I'm going to make them light gray just so I can see them and they pop. So again, lots of different ways to process different types of data in ArcGIS, depending on whether it is gridded, aka raster data, or point lines or polygons, aka vector data. So the next thing we're going to do is we're going to be using this text file that we added. So this is called Ray Precip. I'm going to right click on it, and I'm going to say open. And you can see that it's a table. So we've got some information here. We've got station names over here. These are precipitation stations. We have longitude, we have latitude, we have the annual total precipitation, and then monthly totals of precipitation at each station. So these are long-term averages that have been measured for a number of years. So you're going to close that attribute table. We want to display the locations of this. So we're going to right click, and we have a function here that says display XY data. So my table is correct. I want to call it ray precip sites. Doesn't matter. And longitude is in the right place. X field is longitude, Y field is latitude. And the coordinate system, in this case, is somewhat flexible. We're going to use GCS, the suggested default. And if it looks weird, we can always change this. So I'm going to say OK. And our hope is that when this runs, the points are going to appear in our watershed. And look at that. We ran it. We get some stations. Again, I can't really see what's going on, so I'm going to click on them, make them a little bit brighter. Let's make them red. And this watershed, the reason we use it is because there's a ton of precipitation gauges located in this watershed. That's pretty unusual. But again, it is an intensively monitored watershed. So I also just want to show you, let's zoom in. So let's zoom in on one and let's click it. And all of a sudden you get all sorts of information for that site. You get the longitude, the latitude, and all of that information about annual precipitation. So let's go ahead and zoom out. All right. So let's start processing things. There's a bunch of different ways that we can assess average annual precipitation across a watershed. Many data sets at this point are gridded, but there are places where we have gauge information, which is why I want to talk you through this process, because it is likely that you may have to do this at some point in your future. We are going to open up our ray precip sites attribute table, right click and grab the attribute table. And the easiest way to figure out average annual precipitation across a watershed is just to take a straight arithmetic average. So I'm going to highlight the annual total column. I'm going to right click, and I am going to say statistics. And a bunch of things happen. You actually get a pop-up. This is a neat way that you can interact with data sets. We don't really need it here. It's going to show you like a bar graph of the information. I'm going to close that down. Oh, just kidding. I am not going to close that down. Right click, statistics. Let's try that one more time. If you're ever not sure, you can always redo it. And then over here, I have information that is useful to me. I have the mean of the data set, I have the median, the standard deviation, etc. We care about the mean. So this is your first estimate of average annual precipitation across this watershed. Go ahead and write this down. You're going to need this for later. So we have our average precipitation. I'm going to close this down. Let's assess precipitation totals in another way. So an alternative strategy is what is called Thiessen polygons. This is sort of a nearest neighbor type approach where we're going to draw polygons around each of these circles, places where we have precipitation observations, based on the areas that are closest to those measurements. So this is under Analysis Tools. It is in the Proximity tab, and it is here, Create Thiessen polygons. Our input is our sites data set, and we're going to call this Ray TH poly. And I'm naming it slightly different things from what I say in the handout. It doesn't really matter what the name is as long as you can keep track of what it is. So let's go ahead and say run. And we get our Thiessen polygon data set. But this is sort of not ideal, right? As you look at this, you're like, that doesn't cover the entire watershed. So instead, you're going to keep this output up. And again, it's warning you, it's saying, oh, if you do this, you'll overwrite it. That's okay. I'm going to click on environments, and I'm going to go down to extent. And I am going to say, we want the extent to be RC out, the extent of our watershed. Now let's run that again. Now all of a sudden, we have the information across the entire watershed. So again, we're going to clip this. We want it to be just for our watershed. So I'm going to go back. I'm going to go to extract and clip. And I want to clip my Thiessen polygon data set. And I want to clip it to my watershed outline. And I'm just going to name it Ray Thiessen polygon with a little C at the end. And I'm going to say run. And again, I'm going to get rid of the original data set, right click and remove. And now I have my Thiessen polygons. So each one of these areas is telling us, right, that any area in this polygon is closest to this one station, P053. So some of these polygons are bigger if gauges are further apart. Some of them are smaller if gauges are closer together. So this represents a different way that we can assess how much precipitation we receive across a watershed. So we need a little bit more information to do this. I'm going to have you right click on this. We're going to open the attribute table. And we have a shape area, but we're really not sure what the units of that are or if they're usable. So instead, we are going to calculate that geometry ourselves. So you're going to click right here and you're going to add a new field. All this does is add a column. And I'm going to call this, I'm just going to call this plain old area. And I'm going to say enter. And then under data type, I'm going to make it a double. And all that means it's a number. You have to save. This is the field table. So I'm going to click save up here before I close it. And then when I close it and go back, you're going to see, oh, it's blank. So now we can fill it in. Now we can do something with it. So I'm going to right click on it and select it and then right click. And I'm going to say calculate geometry. So this is really useful if you have points, lines, or polygons. ArcGIS can calculate things for you. So it is telling you the area is right there, and we want a geodesic area calculated in that spot. And let's go ahead and calculate it in square meters, something that we feel comfortable with. And you could specify a coordinate system or more information. We're not going to do that. I'm just going to say, okay. And it is going to give me areas, which is really useful. So what do these areas mean? I want to know these areas and I want to use them to weight my precipitation estimates. So I'm going to open up Excel. And I'm going to go back in here and I want to grab a couple of different things. I'm going to grab object ID, and there's more data down here. Sometimes it's easy to select it all. Sometimes it's hard. I am going to just grab the first 18. Oh, I got it all. Okay, so I've got my object ID field. I'm going to name it. I want to grab my input FID field. Again, I want to select everything. Being a pain, that's okay. Okay, and put FID. And again, to copy it, I'm literally just saying Control C and then Control V. So this is FID, which is a column that ArcGIS usually uses to number things. And then I want to grab the areas. So I'm going to go down here. I'm going to start grabbing from the bottom up. I'm going to scroll up and make sure I got them all. Say Control C to copy, and then Control V to paste. I'm going to name this area meters squared. So the question here is, what does object ID 1 mean? And how do I match this up with my precipitation data? So I'm going to go to rate precip sites. I'm going to open the attribute table. I'm going to do the same thing. I am going to grab the object IDs. See again, 1 through 25. Okay. 1 through 25. Back to here. my annual total precipitation values. Scroll up, copy paste. So this is my object ID. This is my precip. And the question is, how do these match up? And how are you going to figure that out? And so my encouragement here is to actually zoom in on one of the Thiessen polygons. Let's grab this one in the middle. We're going to click on this. We see it's object ID 14 and input ID 9. Input FID 9. Let's grab the precipitation station. It is object ID 9. So that is telling you some information about how you're going to need to move this table around to get the precipitation values aligned with the area values or vice versa. So my encouragement is to take a moment to think about this. When you have these aligned, you are creating a weighted area where you are taking the area divided by the sum of that column. And you are multiplying that by the respective precipitation value in that specific Thiessen polygon. To get the total precipitation across that watershed, you're going to sum all of those values together. If you have questions, again, come see me. I'm happy to chat about it. All right, so we're going to have a different estimate for our Thiessen polygon-based estimation. Finally, we're going to do one more tool. So I tell you on the handout a little bit about spatial interpolation. We're not going to use that approach here. It doesn't really make sense, and I want you to see a third approach that I think is a better approach. Because we talked about how much elevation variation we have across this particular watershed, and it turns out that that's a better relationship for what is happening. So I want to bring in the Word document that I give you. A lot of times annual precipitation is strongly related to elevation. And so here in this figure, I am showing you that average annual precipitation versus elevation for these sites. You'll see it's a fairly linear relationship with an R² of 0.8, which in hydrology world is pretty darn good. And we get a relationship, 0.7721 times X minus 695.88 equals Y. The X in this case is elevation, and the Y is precipitation. So we are going to use this relationship to estimate precipitation across the watershed. So I am again going to activate our tools. I'm going to go over here and I'm going to use a different tool in my spatial analyst toolbox. I'm going to use what is called the raster calculator. So it is under map algebra. I'm going to select raster calculator. What this allows you to do is to write equations to execute calculations. So we are going to use that relationship, and I'm going to grab Ray DEM. Actually, I'm going to grab Ray DEM. You could really grab either of these, but I'm going to show you a couple different things with this. I'm going to grab Ray DEM, and I'm going to use that relationship. Ray DEM times 0.7721 minus, add spaces, 695, excuse me, 0.88. And if this is too small, remember you can always go to the handout to verify this. So I'm going to name this hypsoprecip. This is what is called a hypsometric curve. We're relating elevation to some other piece of information. And I'm going to say run. And it's going to run this for the entire watershed. Oh my goodness. Turns out it ran it for beyond the watershed. So again, we can use what is called the environment tab to restrict what we are doing to just within the watershed. And if you've already executed a command, that's okay. We can rerun it. So I'm going to go over here and I'm going to select mask. And so in this case, I'm going to say mask it to my watershed outline. RC out. I'm going to say run. And it locks it, as you can see over here, because it's saying, oh, I'm overwriting this. And it's running and it's calculating. And it says it finished, but I don't see it. And that is because it is covered up by my Thiessen polygons. So I'm going to pull it up top. And I'm going to right click on it and make it a different color. And you're going to notice some interesting things about this data set, right? In terms of the range and things like that. So think about that as you respond to other questions that I give you. I am going to now grab the information about the average of this data set. So I have hypsoprecip for the entire watershed. I am going to right click on it and select properties. And if I go to, let's say it's on general, I'm going to go to source. And there is information associated with the statistics tab. The mean is going to tell you the mean value for the entire data set. So this is taking basically all of the gridded points. If I zoom in, you can see that hypsoprecip is basically gridded values, and it's taking those gridded values and it's averaging them. So this is your estimate of average annual precipitation using the Thiessen polygon method. And if you've noticed, I haven't mentioned what the units are. So we are in Idaho, and the values that you're seeing are sort of all over the place. And that is because they are in millimeters. So this is not a lot of precipitation that this watershed is receiving. So I ask you to include a few screenshots. I ask you to tell me a little bit about your analysis, the values you got out, and which method you think is the most accurate. Think about all of the information that you have available with this GIS assignment to make that determination. You have just assessed average annual precipitation across a watershed in multiple ways. You can use these same approaches for other watersheds, for other places, and you are good to go.